talked about different ways that you can prove triangles congruent. We talked about 4 different ways. What are the 4 different ways we talked about? SAS, ASA, SSS, and AAS. There's actually one additional way that our book doesn't cover. It's not really looking alive, but it's called the hypotenuse leg. And if you know that you've got 2 right triangles, you can show a pair of hypotenuses congruent and a pair of legs. That'll prove congruence as well. But for whatever reason, that's not on the UI, so I'm going to skip over that. That is another way. Now, in order to prove these triangles congruent, we had to get congruencies from different places, right? I told you to look at the picture and to look for, do they share anything to get a congruency there? Are there any vertical angles to get a congruency there, right? If you've got perpendicular lines, what do perpendicular lines create? Right angles, and right angles are congruent, right? We talked about if you have an angle bisector, that creates 2 congruent angles, correct? And then one of the ones that I did with you guys was the parallel lines cut by transversal. You get a lot of different congruencies. You have that, right? So you're always looking for congruencies. So we're talking about today about isosceles triangles. And we've got some congruencies in isosceles triangles as well. By definition, an isosceles triangle is a triangle with at least 2 sides congruent. And so if you want to talk about the parts of the isosceles triangle, the 2 sides that are congruent are called legs. They're called legs. The angle that's in between those 2 legs is called the vertex angle. The side across from the vertex angle is called the base. And then the angles on either side of the base are base angles. Okay, so that's the part of the isosceles triangle. Now let's say you were doing the proof, okay? And in the proof, they said you had isosceles triangle ABC with vertex angle B, okay? And this right here is triangle ABC. Now, just because it says it's an isosceles triangle, you can't just forget about the fact that the legs are congruent, because you know that they are, but it needs to be stated. So just make sure if they give you this information before you get too far, that you use this information and you state that AB is congruent to CB, and my reason would be the definition of isosceles triangle. Okay? So it says it's isosceles, but if you're going to use the fact that those 2 legs are congruent, that needs to be stated. Does that make sense? It has to be stated. Okay? And vice versa. If you were told that these 2 sides were congruent and you want to say it was isosceles, then you would use the definition there as well. Okay, now, what are some things about isosceles triangles? We have the isosceles triangle theorem, and it says that 2 sides of a triangle are congruent, then the angles opposite of sides are congruent. So we've got an isosceles triangle right here, and we know that these 2 legs here are congruent. This theorem says that the angle is opposite. Okay? When I say opposite, it's where I get across from. It says that those are congruent. Those base angles are congruent. So that's the isosceles triangle theorem. You know, 2 legs are congruent, then the angles opposite of those legs are congruent. So let's look at an example. It says that if GH is congruent to HK, and HJ is congruent to JK, and the measured angle GJK is 100. We want to find the measure of angle HGK, which is this little angle right here. Okay, that's what we're looking for. So we are going to have to go from the right side of this triangle and move our way over to the left. Okay? Now if I look over here at this triangle right here, what kind of triangle is this? It is obtuse, you're right. That didn't really help me too much. What else do I know about it? It's isosceles, right? And we just learned that if you have an isosceles triangle, what do you know about it? That the 2 base angles are congruent. So these 2 angles right here are congruent, yes? And so since this is a obtuse angle, a 100-degree angle, how many degrees does that leave for both of those together? 80. And if they're the same, they're both going to be 40. Okay, good. Okay, so both of those are 40. All right. So now we need to continue our trek over to this other triangle here. What kind of triangle is this? It's isosceles also, isn't it? And so these two angles are going to be congruent. I don't know the measure of any of those, so what might I pick here? What do we know? What can we see? Okay, we've got a linear pair going on right here. So if this is 40, this is going to be 140, right? Okay, and again, these two are the same. How many degrees are left for both of those together? 40, and so each one of them will be 20. Good. Okay, so the measure of angle HGK is 20 degrees. Now, I want to show you something else that you could have done, okay? You may not have recognized this, but I just want to point it out. Let's say if we did not know this, right? Let's say we skipped that step, and we looked at this triangle, and I extended this side. This 40-degree angle is what in relationship to the red one? Equal to what? The remote interior angle, because it's called an exterior angle, right? And remember, your exterior angle is equal to the sum of the remote interior angles. And since this is isosceles, okay, this 40 is going to be those two together, and you can just take half that. It's going to be 20 of those, okay? Now, if you don't recognize that, it's not that big a deal. You can always get it from the other direction, but I just wanted to make sure that I pointed that out to you. All right. We also have the converse of the isosceles triangle theorem. And it says that if two angles of a triangle are congruent, then the sides opposite those angles are congruent. Okay, so this gives me congruent base angles, okay, D and F. And it says that the sides opposite are congruent to each other. Okay, so DE is congruent to FE. Now, we have the isosceles triangle theorem, and we have the converse of the isosceles triangle theorem. How do you keep those straight? Well, what I do is when I'm thinking about the isosceles triangle theorem, it goes back to what is an isosceles triangle, right? An isosceles triangle has two legs congruent. So in the isosceles triangle theorem, you start out with congruent legs, and you can prove congruent angles. And the converse is the opposite, okay? You start out with the congruent angles, and you can prove the legs congruent. Okay, so you got to make sure that you know when to use which one. All right, so let's look at these two examples here. It says, name two unmarked congruent angles. Let's look at that for just a second. Two unmarked congruent angles. What do you think? ACD, no. Because that's not part of the triangle. It is part of a triangle, yes, but not part of the triangle that you're wanting it to be. He's talking about these two angles right here. And yes, indirectly they are going to be congruent to each other. I guess you would be right. Indirectly they would be congruent to each other. But I would have to do a couple of steps to get there, okay? Look at the bigger picture, because you're on the right track. Just look at the bigger picture. Okay, good. If you look at this big picture, okay, and this is an isosceles triangle, so this bigger angle is congruent to that bigger angle, okay? So, angle ACH, right? Would you say ACH? ACH or ACF? Doesn't matter. Angle ACH and angle AFH. Okay, and what allows me to say that? The isosceles triangle theorem. Now, back to what Dawson said. You know what? You were right, because since this big angle here is congruent and these smaller ones are, then these are going to be congruent also, yes? But you would have to do some subtraction and some angle addition postulate. You know, we have to, I mean, if you were able to prove, there'd be a few steps involved there. But you're right, it would. But just be careful, because just because these are congruent doesn't make those congruent. It makes the bigger angle of the triangle. Okay? All right. Now, let's look at two unmarked congruent segments. I think this one's a little easier. What do you think, Sterling?
BC and
look at this triangle here, we've got those base angles congruent, and so that allows us to say that those legs are congruent. So BC is congruent to BF. And what theorem is that? What allows us to say that? So that one's the converse of the isosceles triangle theorem. Good. Okay, let's go to the next page. These next two corollaries, I think you're already familiar with. We've already talked about it a couple times. The first one says that a triangle is equilateral if it is equiangular. So if a triangle is equilateral, it's equiangular, and vice versa. This is a biconditional statement. If it's equilateral, it's equiangular. If it's equiangular, it's equilateral. Okay? So, and I think you've kind of already figured that out. Then it says each angle of an equilateral triangle measures 60 degrees. Okay? So it's kind of using the law of syllogism here, because if a triangle is equilateral, then it's equiangular. If it's equiangular, all the angles measure the same, right? Which are 60 degrees. And so if it's equilateral, each one of the angles are going to be 60 degrees. Okay? And you might need to use this theorem in either one of these corollaries in a proof. Okay? We know it, but there's got to be a reason behind everything we know. Okay, now, before you answer this, I want you to be prepared to justify it, okay? Because you can kind of look at it and see it, but I want you to be able to explain it to me, okay? It says find the measure of each. You want to find the measure of angle Y. What do you think? Right. It is 60 degrees. Why is it 60 degrees? Very good. Okay. Because this is an isosceles triangle, you can use the isosceles triangle to prove those two angles congruent. Okay? There's 120 degrees left for both of them. Divide that by 2, then there's 60 degrees. Okay? So then, what about YZ? What's it going to be? Okay? It's 8 inches. Very good. And why is that? So if it's equiangular, it's equilateral. Very good. Very good. Okay. One more. Find the value of each variable. What do you think? What kind of triangle are we dealing with here? It's isosceles, right? So since it's isosceles, what does that tell us? The two base angles are congruent. Okay? And so they're both going to be 2x, which tells us what? X equals 30. You're right, but because they're all 2x, that makes it equiangular, which means all of those angles are 60. And if we divide by 2, we get x is 30. Okay, and so since it's equiangular, it's also equilateral, right? And so to figure out y, I'm going to set 4y minus 5 equal to what? So add 5 to both sides, and y is 2. Okay. Now, in one of my hours today, they got really mad at me because I made them explain to me why. Because they looked at that and said, there's got to be a reason why behind everything, right? You know, a couple years ago when Common Core was coming along, it kind of got a bad rap, but there were some kind of good things about it. How many of you ever got something right, but just lucked out on getting it right? Has it ever happened to you? Okay, you didn't really understand what you were doing, but you somehow got the answer right, yes?
Oh, yeah.
Okay, that was one good thing about Common Core, is it made you explain why. And if you can explain why you got it, then you really understand it better than if you just by chance get the answer right, yes? Yes, okay. So make sure that you understand the reason behind the answers that you're getting. We learned about an isosceles triangle and equilateral today, and we said that, what does the isosceles triangle theorem tell you? About these two legs are congruent. What does it tell you? The base angles are congruent. And then the converse of the isosceles triangle theorem tells me what? If the base angles are congruent, then the legs are congruent. And so if the triangle is equilateral, it's equiangular. And if it's equiangular, it's equilateral. In an equilateral Draw a triangle with the angles measured. 60 degrees. Okay? Any questions? Alright, your assignment is on page 289.